Chapter 5, Lesson 6. We're going to be talking about the derivatives of all the inverse trig functions. Now, I want you to take a look. I am going to write these interchangeably. If you recall from pre-calculus, arcsine is just another way of saying the inverse sine. Inverse tangent is the same as arctan. Arcsecant is the same as inverse secant. Please take a close look at these three rules. Notice I already wrote them in the form of chain rule. If you happen to have another function inside of here, this is your essential rule for arcsine. But if you need to use the chain rule, don't forget to multiply by the derivative of whatever function u represents. Same thing for tangent and arcsecant. So if you take a close look at those three, you'll realize that the other three trig functions are very similar. Please notice the derivatives for arccosine and arcsine are the exact same, except arccosine is a negative. The same thing goes for the derivatives of arctangent and arccotangent. The only difference is a negative. Same thing for arcsecant and arccosecant. So all the cos happen to have a negative in them. Otherwise, they're the exact same formulas. And you might be asking, how on earth did we get these derivative functions in this form? That doesn't seem to make any sense compared to what we know. Unless we take a look at arcsine here. If I were to take the derivative of both sides, I don't really know what to do there. But what if I were to rewrite this? Technically what I'm doing is I'm taking the sine of both sides. And I know that the sine of arcsine, since they are inverse functions, will wind up being just sine of y equals x. Now we're going to take the derivative of that. Notice that when we take the derivative, we have to derive implicitly. Do not forget your dy dx. Now, in solving for dy dx, we get 1 over cosine of y. That still doesn't look like my original function up there on the left, the derivative of arcsine. But when we decide to rewrite this in terms of x, you'll find something surprising. When I'm looking at sine of y equaling x, that would let me know, since sine is the opposite side over the adjacent. When I have sine of an angle y degrees, or y radians, the opposite side over the hypotenuse, sine is opposite over hypotenuse, I hope I said that right a minute ago, would be equal to x. Using the Pythagorean theorem, if we're trying to solve for that third side, I know that the square of one leg plus the square of the other leg equals the square of the hypotenuse. Doing a little bit of solving, I find out that that third side is the square root of 1 minus x squared. Well, ladies and gentlemen, that brings us to a conclusion. If this other leg is 1 minus x squared, that third side, the opposite being x and the hypotenuse being 1, if the third side is the square root of 1 minus x squared, that would mean that cosine of y is equal to the adjacent over the hypotenuse, or 1 minus x squared. That's how we get the formulas for all 6 of these arc or inverse trig functions. You could do the same derivation for each one. I'm not going to ask you to do that, and I'm not going to do it for you right now. You might want a few examples, though, of how to use this. Example 1, arcsine of 5x. Applying the formula that's up there, everywhere you see a u, please put 5x. Anywhere you see u prime, take the derivative of 5x. Please remember, when you simplify, the 5x squared means 5 squared and x squared, not just one variable or one number squared. That's the final answer in purple. Next example. Notice for this one I wrote inverse cosecant. That means the same as arccosecant. Please take a look at the rule over here on the left. Everywhere you see a u, plug in x over 8, and u prime, plug in 1/8. Something like that. It's going to take a moment to simplify this one because of the complex fractions. Notice in the absolute value of 8 is just plain old 8, and I did find a common denominator in the square root. And then we simplify. Ta-da!